Hello guys, welcome to my channel Read NCERT Physics with Shivam. And in this video we'll start a new chapter number 2, Electrostatic, Potential and Capacitance. I will explain to you in English on the request of one of the students. So we start. We'll first look at the first paragraph, that is the introduction paragraph. So I'll read the NCERT line by line and explain the meaning to you. Okay, so the first line is, in chapter number 6 and 8, the notion of potential energy was introduced. When an external force does work in taking a body from a point to another against a force like spring force or gravitational force, that works gets stored as potential energy of the body. As you have read in class 11, when you take like there's a mass here on the ground, and you put this mass, you lift this mass up to an height h, suppose an height h. So what you are doing basically, so there is a force of gravity. Okay, you are doing work against the, you are applying force, you are doing the work against the force of gravity. So in this process, when you are doing work, this work is being stored as potential energy of the body. So in lifting the body up to an height h, you have done certain work against the force of gravity, and this work has been stored in the form of potential energy, that is called the gravitational potential energy. You know about this. Okay, similarly in the case of a spring. Okay, there is a spring. So what you do, when you apply a force on this, you deform this spring, you apply a force, it gets like this, it compresses, and on compressing you have done certain work, okay, against the restoring force. Okay, so this force, this work has been stored in the form of potential energy. In this case we call it elastic potential energy. You know about this thing. Okay, so we'll draw analogy from this and try to understand what a electrostatic potential energy is, electrostatic potential and potential energies. Okay, just remind this two examples, keep in mind these examples. Now the sum of kinetic and potential energy is thus conserved. So what happens, similarly, if you look at this line, when the external forces remove, the body moves, gaining kinetic energy and losing an amount of potential energy. Okay, so what happens, if you like, you have put this box up to an height h, and when you released it, this box from the height h, what happens, this box falls, this mass falls. Okay, so you have done certain work and it was stored in the form of potential energy, and when you release it, the potential energy just start converting into what, it is losing energy. Okay, it is coming down and it is losing energy. Okay, so and it is gaining kinetic energy at the same time. Okay, the amount it loses potential energy, same amount the kinetic energy increases. So the sum of this kinetic and potential energy is always a constant. So we say that the potential energy and kinetic energy is conserved. Okay, I can give you an example, like I can give you a number, just a vague number. For example, there was a 20 joule potential at this point. At this point it was at rest, suppose. Okay, and there was 0 joule kinetic energy. So the total energy kinetic plus potential was 20 joule. Okay, suppose it falls down at a height, this much height, and suppose only it loses 10 joule energy. Okay, and the 10 joule energy will be converted into 10 joule kinetic energy. Okay, so this is a transformation of energy going on. You know about this from your earlier classes. And forces of this kind are conservative forces. So one important point is that such kind of forces is conservative forces, in which one energy is the total energy is conserved. Okay, the total energy conserved. And you also know about conservative forces, in which this is past different independent. Okay, it doesn't matter if you take this box from this part or this part or this part, only matters is the initial and the final position. Okay, you know about all these things from your 11th class. Spring force and gravitational force are examples of conservative forces. Okay, the two examples we discuss are examples of this kind of forces, conservative forces, part independent. Okay, now conservative force between two stationary charges is also a conservative force, Coulomb force. Okay, similarly we'll add another force in this list. Okay, so this is the Coulomb force that we studied in the chapter number 1. So the Coulomb force between two charges is also conservative. Okay, that is, it doesn't depend on the path, and the total energy, potential and kinetic energy, will be conserved at all points. Okay, This is not surprising since both have inverse square dependence on distance and differ mainly in the proportionality constant. The mass in the gravitation law replaced by the charge in the Coulomb's law. Okay, as we have seen in the first chapter. So what is the formula for potential Coulomb law? So the formula was K is equal to 1 up F is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon r square. Okay, where q1 q2 are the magnitude of the two charges and r is the distance between the two charges. Okay, and this is 1 4 pi epsilon naught. Epsilon naught is the, this is a constant, this is the permittivity. Okay, so you see, this was I made the chapter in Hindi. I will also make this in English too. Okay, so this is the formula for force between two charges, Coulomb force. If you see, in gravitational force, the formula is, you know from class 11, g m1 m2 upon r square. So you see that there's a similarity, both follows inverse square law, and their constant has been replaced by another constant here, and the magnitude of charges has been replaced by masses, magnitude of masses. So there are a lot of similarity, and so that's why you won't be surprised that these both are conservative forces. Okay, thus, like the potential energy of a mass in gravitational field, we can define electrostatic potential of a charge in an electrostatic field. Okay, so similarly, the same way define potential energy of a mass in a gravitational field. Okay, we can define a potential energy. I will see now. Okay, how will it define? The work done will define. Okay, so we'll take we'll read. I will go to the next paragraph. Consider an electrostatic field E. This is a vector E vector due to some charge configuration. Okay, so this is a diagram of this. There is charge Q. Okay, and it has certain field. As you know from chapter 1, the electric field will be in outward direction, away from this. Okay, you know how do we come to know about this? Because if you place a positive charge, test charge, then it will be repelled. Okay, so this is the electric field direction. The electric field will be like this. So for simplicity, consider the field due to charge q placed at the origin. Okay, so we have placed the charge q at origin. Okay, that plus q at origin. Okay, capital Q. Now imagine that we bring a test charge small q from a point capital R to a point P against the repulsive force on it due to charge q. So now what we'll do, we'll bring a charge small q. Okay, so what we'll do, there's a 2 point in this. We are bringing a small charge from this point to this point. So you see the force, the electric field is in this direction, and if I bring a positive charge against this force, so I have to do work because it is a repulsive force and I'm going against it. So I have to, this is exerting a force on this, the Coulomb force, and I have to go against it. If I have to bring this charge from R to P, I have to apply a force which is opposite in direction to this electrostatic force. Okay, so yeah, so with reference to figure 2.1, this will happen if q, capital Q and q are both positive or both negative. Okay, this situation will arise if both are of same type, that is positive positive, negative negative. Otherwise the system, this charge will attract it. We will not talk about that. We will just talk about that these two force charges are of same type, that is positive, either positive or either negative. Only then it will repel. We can talk about the other way, both opposite charges, but you will understand if you come across this. Okay, for definedness, let us take capital Q greater than 0. Okay, two remarks may be made here. First, we assume that the test charge Q is small q is small, that it does not disturb the original configuration, namely the charge Q at the origin, or else we fix Q at the origin by small unspecified force. Okay, so what we'll do, we'll take the test charge, the small q charge as small. And why are we doing this? Because you know, if we are taking this magnitude of this charge is large, then what happens? It will exert a force on this and will disturb its is electric is region, or okay, it will exert force on this. Okay, so we don't want that. We are just studying the effect of this on this at this point. That's why this is a test chart, and we should always keep the test chart. Okay, this chart should be close to zero, limit tends to zero, that is the chart should be as small as possible. Okay, another way we can do another thing, if we can fix this position of this chart by any other type of force, that way also work. Okay, but we'll keep the magnitude of this test chart small, so that it does not disturb this configuration. We don't want to change the, we don't want this configuration, that is the position of plus q to be changed. Okay, so uh, second, in bringing the charge small q from r to p, we apply an external force F external, just enough to counter the repulsive force Fe. Okay, so what we'll do, will, as I told you, that we'll apply another force, external force, in opposite direction to the repulsive force that this charge is applying. This plus q charge is applying a repulsive force. Okay, and we are applying, in order to move this charge, we are applying a force external force that is equal and opposite to this force. Okay, so why equal? Opposite we understand, we have to move is against this, but why equal? So that you see here, this means that there is no net force on acceleration of charge q when it is brought from r to p. It is brought with infinitesimal slow constant speed. Okay, so what we don't want is to it to be accelerated. Okay, suppose it is applying 10 newton force, and if we apply suppose 11 newton, okay, 12 newton, so what will happen, there will be a net force in this direction, and if there is a net force, the charge will be accelerated when we don't want that. Okay, so we don't want the charge to be accelerated, so we'll apply equal and opposite force, so that the charge doesn't get accelerated, and we bring it a very small speed, very infinitesimally slow constant speed. Okay, we don't want the charge to be accelerated. Okay, in this situation, work done by the external force is the negative of the work done by the electric field. Okay, so you can see there, okay, the charge, we are doing certain force, we are doing certain work because we are applying force, so there is a work, we are doing a work against the electric field, and this is the this is opposite to the work done by the electric field. Okay, and yeah, if you see the next line, if the external force is removed from reaching point P and it displays line and gets fully stored in the form of potential energy of the charge. Okay, so as I told you in the gravitational example, if we are taking a mass to a certain height, then what happens, that work then will be stored as potential energy. Similarly, in this we are doing work against that electric field, so that work is stored in the form of potential energy, electrostatic potential energy in this case. Okay, I hope this is clear to you. Now if you see, uh, yeah, we'll move to the next line. If the external force is removed on reaching P, the electric force will take the charge away from Q. The stored potential energy at point P is used to kinetic energy to the charge q, small q, in such a way that the sum of the kinetic energy potential energy is conserved. Similar to the example that we did earlier, if we it says that if you just bring it to this point, okay, and then release it, so what will happen then? In that case, now this, there is no external force now. Okay, because we have left it, then this charge, this electric field, this force will take charge and it will push it away. Okay, so the potential energy that has been stored, because of the work done, what we did, will take this away from this, converting the potential energy into kinetic energy. The charge will start moving, and in such a way that the sum of potential energy and kinetic energy will be a constant. Okay, that was the just the definition of conservative force. Okay, yeah, now we'll move to the next line, and yeah, yes, this was the line, and at P is used to provide kinetic energy to the charge in such a way that the sum of the kinetic and potential energy is conserved, that I have told you. Now, thus the work done by external force in moving a charge q from r to P is work done r P is integration of external dot dr. Okay, suppose we move a small distance dr, infinitely small distance dr. Okay, and Okay, so what will be the work done by us? So F work will be, for this small distance, the work done, for the small distance the work done will be F external dot dr. Okay, so this will be the work done. I can write in vector form. Okay, because the two direction, F external is in direction, displacement is also in this direction, so this is F external dr cos 0, and cos 0 you know is 1, so work done is this much. Okay, but if you see, the work done and the total work done, so this is this very small work done, and the total work done from R to P will just be the integration of F dr. Okay, F external, mind you this is F dr, F external. Okay, this is work, total work done from R to P. Okay, you know about this. Okay, we just integrate. Okay, now okay, and for work done, and this will be equal to, you know, F external is equal to the that electric field, electrostatic force. So I'll put in place of external force, I'll put minus F, that is the electrostatic force dr. Okay, yeah, and yeah, this will be the case from R to P. Obviously the limit will be from R to P. Okay, so this I have told you. Now this work done is against electrostatic repulsive force and gets stored as potential energy. Okay, and this will be, I have told you this. Okay, the repulsive force is stored as potential energy. Now at every point in the electric field, a particle with charge q possesses a certain electrostatic potential energy. This work done increases potential energy by an amount equal to potential energy difference between different point R and P. Okay, so you see every point it in moving a certain distance towards this charge, we are doing certain work. So every point has a potential energy. If the charge is placed here, it has certain energy, potential energy, it has certain energy. So if it is moving certain distance, then the work increases. Okay, the work increases, and the potential amount of potential energy gained by the charge also increases. Okay, I think you are understanding. Okay, now then we have, okay, yeah, then the potential energy difference, and the that potential difference will be up minus ur. Okay, suppose to understand this, let us take suppose this has point, suppose this has potential energy, suppose this is potential 20. Okay, suppose it has potential energy 30. So what is the potential difference between 2 points? Just subtract them. Okay, just subtract them, that is the 10 is the potential difference between 2 points. That is 10 is what the work done in moving the charge from this point is 10 joule, whatever you can there say. Okay, so now you understand. Okay, I think you are getting it. Now next is, note here that the displacement is an opposite sense to the electric force, and hence work done by the electric field is negative. It is clear that work done will be negative by electric field, obviously. So okay, so whenever there is a minus sign in this, it implies that work is done by the electric field. Okay, and plus will be that electric, we are doing the external work. Therefore we can define electric potential energy difference between 2 points at the work required done to be by an external force in moving without the accelerating charge q from one point to another for electric field of an arbitrary charge configuration. Okay, so you can have understood that what is the potential difference between 2 points. It is the work done in moving a charge, unit positive charge, in an electric field. Okay, without acceleration. Okay, now next, two important components may be made at this stage. First point, the right side of equation 2.2 depends only on in the initial and final position of the charge, and it means that the work done by an electrostatic field in the moving a charge from one point to another point depends only on the initial and the final position, and it's independent of the part taken to be from one point to another. Okay, so as we have told, I already told you that this is from equation also you can see this work done only depends on the position rp, the points p. Okay, the distance of the two charges. Okay, the position of the two charges, 2 points. Okay, so this is path independent. It doesn't matter from which part you bring this point from R to P, only matters the two points, the position of the 2 points. So this is and this is the property of what? Conservative force. So this is the fundamental characteristic of a conservative force. The concept of the potential energy would not be meaningful if the work done depended on the path. Okay, so potential, okay, so potential energy doesn't depend on this, doesn't depend on the path. The path independence of work done by an electrostatic field can be proved using the Coulomb law. We omit this proof. Okay, by Coulomb law we can prove this path independence, but it has omitted it, so I'll move to the second point. So second point is equation 2.2 defines potential energy difference in terms of the physically meaningful quantity of work. Okay, so what it has done, it has potential energy difference is been defined in terms of work done in moving the charge from one point to another. Clearly potential energy of so defined is undetermined to within an additive constant. What this means is that the actual value of potential energy is not physically significant, it's the only difference of potential energy that is significant. Okay, so this is very important. You have to remember, important thing is potential energy difference between 2 points. Okay, so what is the potential energy difference? The work done in moving from one point to another. Okay, so it is not work done, just say work done, potential energy. Important is potential energy difference. It will tell you about the from where 2 points you are moving the charge. Okay, so it is important. Even potential energy, when you are saying potential energy, it means that you have done certain works. At that case you can choose the generally we choose the second point, infinity. We bring charge from infinity to one point and we say that we have certain potential energy. So what we have done, we have bring the charge from infinity. Even then there is a potential energy difference. Okay, so potential energy is the energy difference is the main thing. Okay, and we have made is potential energy, so we have for infinity. Okay, even that concept is we can take any 2 points. Okay, the important thing is potential difference. Okay, now it is only the difference between of potential energy that is significant. We can always add an arbitrary constant alpha to the potential energy at every point, since this will not change the potential difference. Okay, so what I can do, like here you can see I say there is a potential of 20, there is potentiality of 30. If I add 10 some constant, suppose 5 and 5, so it will not change the potential difference. The potential difference will be same, that matters. Okay, so you have done the similar thing. Up plus alpha minus ur plus alpha is equal to up minus alpha. The potential difference will be same. Okay, okay, so now put it differently, there is a freedom in choosing the point where potential energy is 0. So you see, it is not very necessary that we choose a certain point where potential energy is 0. Even generally we choose infinity as potential is 0, we can choose another point. Okay, then but even we choose potential is 0 at a different point, not an infinity or at different point, it will not matter, because we are concerned with the difference in the 2 points. Okay, and not the point, only single point, 2 points, that is the potential difference will not be affected. I hope you are getting my point, because I'm not able to speak properly in English, so just trying to explain. To try to understand it, just read the book once and you will get it. Okay, so the important thing is you are the difference in potential important. Put it differently, there is a freedom in choosing the point where potential energy is 0. A convenient choice is to have a electrostatic potential energy 0 at infinity, but we generally choose infinity as 0. Okay, with this choice we take the point r at infinity. Okay, we are taking the r at infinity, so then work done will be infinity p up minus u infinity and the infinity. Okay, so this will become, so what we are doing, we are choosing the r is infinity as 0 potential. We can choose any point, it doesn't matter, as I told you. Okay, so this will be 0, so work done will be up. So now we can define the potential. Okay, potential energy, since the point p is arbitrary, provides us with the definition of potential energy of a charge q at any point. Potential energy of a charge is a point in the presence of field due to any charge conveys the work done by the external force in bringing a charge q from infinity to point. Okay, so what is the potential energy of a point? Potential energy is a charge kept at the point. Potential energy of charge kept at the point p will be the work done in bringing the charge from infinity to that point. This is the convention we have followed. Okay, and it is not necessary that we choose infinity here, but this is the convention we follow, so we choose infinity as zero potential. Okay, and this is definition of electric potential energy, okay, of a charge at any point in the electric field. Okay, I hope I was able to make you understand this NCERT first paragraph of this second chapter clear. Okay, if you have any doubt, you can ask in the comment section. And I'm trying to. My English is not very good, but I'm trying my best to make you understand. Okay, so and you can give me any feedback you want. You see you any modification that I have to do in my videos I can improve my content. Okay, and if you come across any mistake in my explanation, I try to not to commit any mistake, but if by chance I make mistake, then you can comment in the comment. Okay, then I will try to omit that mistake, and others will come to know about that, so that everyone will understand the right physics. Okay, and thanks for watching this video.